Hey everybody, thank you for joining us for this month's webinar. Today we're going to be talking about or sharing one of our strategic partners with you, which is Cockroach Labs. I think one of the reasons they make such a great partnership with Erlang Solutions is that we are obviously all about providing the most scalable solutions possible to large, ambitious organizations. And what working with Cockroach Labs allows us to do is to make sure that our databases meet the standards of the rest of our systems, to make sure that there are really resilient, fault-tolerant, end-to-end systems where every component is able to meet the kind of loads and spikes in users that we would expect of any of our systems. And so today we have Daniel Holt from the Cockroach Labs team, who will be taking you through a technical deep dive about the decisions they've made that allow them to offer such great solutions for their databasing. So with that, it's worth remembering that at the end we'll have a Q&A. So if at any point you have a question throughout, you can put it through via Twitter or via the GoTo platform, and we'll ask that to Daniel at the end. So you can either save it up or send it through live, and we can ask it at the end. But with that, I'll hand over to Daniel, who'll take you through CockroachDB and how it works.
Thank you very much. Hi guys. Yeah, my name is Daniel Holt, and as mentioned, I work for Cockroach Labs. My official role here is Director of Solutions Engineering for the international organization. And for the past, I'd say over 15 years, I've worked in the database space. For the past 10 years, I've focused more deeply on sort of cloud native technologies. Worked for various companies in the past, such as Microsoft and a company called Pythian, DataStax, lots of well-known sort of database platforms. So I do have a wealth of experience that I'm willing to share with the community. And as mentioned today, I'm just going to give you an overview and a slightly deeper technical overview of CockroachDB and some of the benefits that we believe it brings to not just developers like yourselves, but to the customers that we are ultimately serving as well. So what is CockroachDB? I always like to start with this question. I often get asked, is CockroachDB just another database? And the short answer to that, yes, but it's another database with a very unique set of features. So CockroachDB is actually a globally distributed database that was built predominantly to help with cloud native type of workloads. Think of CockroachDB and when you want to use CockroachDB, when you want to keep things like transactions, you want to keep accuracy of the data in terms of your data consistency, but you want to do that at massive scale. Now, you can start very small with Cockroach, but it does allow you to achieve quite massive scale with things like concurrency as well as resiliency, all built into the product by default. In terms of why you would use CockroachDB, like I mentioned, if you need consistency of your data, and we will dig into what we actually mean by consistency and what the different databases offer in terms of consistency as well. But more importantly, if you want consistency at scale, is where Cockroach really shines. If you also want to guarantee certain survivability criteria, there's a lot of talk when you go into organizations around business continuity plans and disaster recovery scenarios and things like that. So if you guys wasn't aware, just a fun fact for you, the actual name comes from the survivability characteristics of the cockroach. In the means that everybody jokes that cockroaches will be the ones that outlast us all, even in the events of nuclear holocausts and things like that. And as long as you architect this database properly, you can survive that as well. The other benefit of cockroaches is they tend to go in and colonize every little piece of hardware that you can use. So if you want to throw 50 nodes at CockroachDB, we will use all of that available resource by being a multi-active database. In terms of the very unique features that we have, we'll come on to more examples of this later, but we have a feature called GDPR, which allows you to give locality to the data that you're storing within the database, which allows you to do very clever things around latency when you're running in a distributed environment. It also allows you to comply with some laws, such as GDPR, the California Data Protection Act, and things like that. And we can run pretty much everywhere, as you can see from the diagram at the bottom right here. We can run in public cloud, private cloud, on-premise, and Kubernetes, on virtualization. You know, any hardware that you have, we pretty much run on top of it. So I often get asked what are some common applications that people are running on top of CockroachDB. And as you can imagine, being an OLTP database as opposed to an OLAP database, we're getting a lot of system of record workloads, things like ledgers, both financial, inventory, and payments. Identity access management and metadata type of use cases are also very big with us. And we're seeing a lot of companies adopt us as the database of choice for an underpinning software as a service platform, like a database as a service for private clouds and things like that. As mentioned earlier, if you need to apply any locality awareness to any of your data or your nodes, then Cockroach is pretty much one of the only databases that can allow you to do that with ease. And with the latest release of 21.1, which was released today, we've made that even easier. In terms of where we see the migration side of things, we're seeing a lot of people move away from some sort of traditional legacy databases because of the lack of scale that they offer. And on the flip side of that, where people go to for scale is predominantly NoSQL databases. But by doing that, they've already lost the consistency guarantees that come with a traditional database. So we really are the bridge between those two legacy technologies, you know, the NoSQL, the scalability, and the ACID compliance, the transactional consistency of relational databases. So this is just a splash side of some key features that we have. This is to show that we are a fully featured database that has everything from encryption at rest, security features, you know, the ability to import and export data at scale. Some of the newer features that we've implemented are things like vectorized SQL execution engines. This really helps with those, you know, aggregation type queries. So if you have an end of day aggregation that you need to run, a column store type of vectorized execution engine really helps speed up those things. So we really are on the cutting edge of you know, on the bleeding edge of this technology, and we're driving the market forward with these features. So let's talk a little bit about the technology now and get into sort of a high level architecture. It's important to know that CockroachDB, all nodes share, it's a shared nothing architecture. What that means is node 1 shares nothing with node 2, shares nothing with node 3. So we really can treat these nodes as cattle as opposed to pets. So there's no centralized server. It's a decentralized cluster with no single controller there. The nodes are also have awareness of itself and the other nodes around it, which gives way to some very unique features like the geo-partitioning that I talked about earlier. In terms of how we replicate data, by default, out of the box, data is replicated at least 3 times. We call this the replication factor, but that is configurable depending on your survivability criteria. We're a quorum-based system or a consensus-based system, and the algorithm we use to ensure the consistency and replication of the data is called RAFT. You may have heard of RAFT because etcd uses it as well. What we did was we took the etcd's version of RAFT and we modified it to be way more performant running at scale. And I'll touch on that in a little bit as well. We've architected the database to specifically handle latency between nodes, but more importantly, between nodes in different disparate regions as well. So we can be very, very flexible and tune the performance characteristics depending on your requirements. As I mentioned, we're always consistent in terms of data accuracy. If you're familiar with the ACID concept, we run in serializable isolation level, which is one of the top isolation levels that you can run up in a database to ensure that, you know, all of the data stored within CockroachDB is always up to date and always consistent. The other thing to mention is it's a very clean installation, and coming from a very DevOps background myself, I really like this about CockroachDB. I mean, it's a single binary, it has no dependency, and the only requirement is to open 2 ports in terms of the networking. So if you guys or if anybody is using a sort of CI/CD pipelining with Jenkins or Terraform or Ansible or Chef or Puppet, this is super easy to integrate with those technologies. I'm going to talk a little bit about the diagram on the bottom right-hand side, because I think it's important for you to understand the makeup of the actual binary itself. Right at the bottom, we have a data tier, and you may be surprised to know that we're actually a key value store underneath the hood. We used to use RocksDB in previous releases. In the last 2 releases, we've actually created our own key value store called Pebble, and we actually use a key value store for its atomicity and distribution purposes. It's also very, very performant type of database when you're running in this distributed fashion. That key value store, though, is never exposed to end users, because that would just add complexity to the users. So the only way that users can actually work with that key value store is through a SQL API. And the SQL API that we've chosen to use is Postgres. So we speak the Postgres dialect of SQL, and we're also Postgres wire compatible. That means any third-party tool, any ORM, any programming language with a Postgres compatible driver will be able to talk to CockroachDB with no problems at all. The other things that make us up, they call it sort of the global coordination piece here. What that essentially is a set of database heuristics that help manage the database automatically for you. So think of scaling. When you add a node, the database takes care of redistributing the data to make full and effective use of all of that hardware that you've just applied to the cluster. We also do some very clever optimizations at that layer as well, regarding moving leases around and moving ranges around, and we'll talk about what a range is in an upcoming slide as well. On top of that, as you can imagine, we have a security tier, and the security tier is something that you're probably all familiar with other database technologies. Things like role-based access control, encryption at rest, encryption in flight, things like that are all built into the product, and very similar to the way that Postgres handle things as well. So very familiar for developers. The optimization piece is really important as well, and this is where we really differentiate ourselves from a lot of the market. We've actually spent the first, I'd say, 4 years of developing CockroachDB, spending a lot of time building our own cost-based optimizer. That gives us a lot of flexibility in managing sort of latencies and performance, because we can tune things at a very granular level, right down to the optimizer's operator level. In terms of management, we do have a database console where we expose to show you a load of time series data, CPU utilization, RAM, network, but also a lot of application level data, like what applications are running what queries and what latencies those queries are seeing from the database perspective. We also store things like execution plans in there so that you can actually see and help you tune those environments or those problematic queries to be as efficient as possible. In terms of integration, there's a number of integration points that we have in terms of getting data out of CockroachDB, because we also understand that CockroachDB is not the silver bullet that is going to solve all of your use cases, so you may need to move data out of CockroachDB as well. For that, we have integrations into Kafka via a feature called Change Data Capture, or CDC. We also expose Prometheus endpoints for monitoring. So if you guys, or if anybody has a sort of Prometheus Grafana alert manager stack, or most third-party monitoring tools will have some form of Prometheus plugin, we'll be able to work with CockroachDB as well. The last integration that's probably prevalent here is the one of Kubernetes. So we actually run natively inside of Kubernetes, because when we were architecting CockroachDB as this shared nothing sort of architecture, we were keeping Kubernetes in mind, because we believed that the way most companies going forward was to be developing microservice type applications. So let's talk a little bit about how data is written in CockroachDB and how we do things like replication and distribution. So in CockroachDB, there's a concept of a range. Now, a range is basically a contiguous 512 megabyte block, but it's important to know that all of these ranges are always lexicographically ordered, and the reason that's important is because it makes us very efficient and very flexible, similar to a SQL database in terms of doing things like range scans and things like that. In terms of why 512 megabytes in size, you may ask, Well, the answer to that is the ranges are small enough so that we can move them around nodes and move them around networks very, very quickly. But they are large enough that we can amortize any indexing overhead that we need to, because there is an index in front of each range. You can think of it as kind of like a B-tree index, but it's not quite a B-tree index, but it works in a very similar way. So it's important also to note that most operations in CockroachDB are done at this level. It's done at the range level. So I talked about us using Raft previously, and if you guys have any experience with Raft, you will understand the concept of Raft groups. So a Raft group in CockroachDB is at the range level. So the Raft group is essentially the range and its replicas. So let's talk a little bit about the basics. So I've mentioned that the default replication factor is 3. So that's what we're going to go with through the slides here, but that is configurable. And obviously, because we are a consensus-based algorithm, it doesn't make sense to have even numbers. So when you're changing replication factor, it's always good to keep an odd number. So 3, 5, 7, 9. And that replication factor is also very configurable down to a table, a row, or a partition level as well. So it is really configurable. And each of those ranges are then put on separate nodes. We will never allow multiple ranges of the same Raft group to be on the same node for resiliency purposes. So in Raft, there is a concept of a Raft leader. We call it a leaseholder, but it's essentially one of the 3 replicas in this Raft group will be elected as the leaseholder, and that is the concept that governs the reads and writes for this particular range group. We will go through a write and a read path, but it's important to know that we do something called a leaseholder check every 9 seconds. So if a leaseholder isn't available for 9 seconds, then it automatically gets elected as another replica as part of that Raft groups. This allows us to do things like atomic writes across Raft groups and things like that. So let's take an example of a write operation. So you have your user here who will hit a load balancer and then get routed to what we call as a gateway node. From that gateway node, we will forward the request to the leaseholder, and the leaseholder will write the data to its Raft log. Once it's done that, it will send out simultaneous requests to the other 2 nodes that hold the replicas for this range. And the quickest one to return, as long as one of those returns, we've achieved a quorum. So that's 2 out of the 3 replicas has now been written to their Raft log, and we can consider that as a successful write because we've achieved the quorum. We will send that back to the gateway node and then eventually get back to the client to say that that's been successful. The 3rd replica is then asynchronously updated, and then all 3 replicas are in check and in sync. In terms of a read path, it's a lot simpler than a write path. Because we've done that consensus or that quorum operation on the write portion, we can guarantee consistency on the read portion by just getting the data from the leaseholder, because that leaseholder knows exactly the up-to-date data. So if we have a look at that as a diagram, you'll see it hits a gateway node again. It will go to node 4 in this case, which is the leaseholder. It goes back to the gateway node and then back to the client. So a very, very quick operation there. It's also a good time here to advise that CockroachDB is an MVCC store. So it's a multi-value concurrency control store, which means we store historical data for up to 25 hours for any given row. After 25 hours, garbage collection kicks in, and then we physically remove that from the database. That gives you the ability to do time traveler queries, or what we call follower read queries. Now that's slightly different to the operation that we've just gone through there. What a follower read or a time traveler query will do, it will allow you to read data from a replica, not just from the leaseholder. There is a caveat to that the data can be up to 4.5 seconds old, but if you can accommodate some staleness in the data, then that is another way to speed up read operations within CockroachDB. Okay, let's talk about the fun bits. Well, what happens when nodes fail? So There are two types of operations or two types of failures that we see in CockroachDB. There are temporary failures, and then there are more permanent failures. So if we take an example of a temporary failure, for us, by default, that's a node that goes down for less than 5 minutes. If the node comes back up within that 5-minute period, we will automatically catch that replica up with the checksums or the deltas from the other replicas within that range group. If it goes beyond 5 minutes time, we will consider that node as completely dead, but we also realize that you have to maintain a replication factor that you've set. So we will create another copy on another node to always maintain your replication factor and keep you as resilient as possible. The setting that you see in the third bullet point here is configurable, and that's that 5-minute setting that I was talking about. So if we have a look at a non-leaseholder node failure here, so node 1 is going to go disappear. What happens is after 5 minutes, we realize that node is dead, and then we will create a new replica on node 3, always maintaining your replication factor, always maintaining your survivability guarantees, and making sure that you're resilient as possible. But that was easy because that was a non-leaseholder node. So what happens if we lose the actual leaseholder node? So very similar, the node goes away, and this is where that 9 seconds comes in. As part of the Raft protocol, there is a leaseholder election function. That runs every 9 seconds for CockroachDB. So once node 4 disappears here, within the 9 seconds, we will select a new leaseholder. In this case, it's node 1. And then 5 minutes later, again, we will add a new replica, always maintaining that resiliency factor for you. There are two things to note here. Firstly, any in-flight transactions to that leaseholder node that disappeared will need to be retried. So we will throw an error back to say you need to retry the transaction because we can't reach the leaseholder. When you retry that transaction, it will hit the new leaseholder, and then the application will make forward progress. So one thing that you have to do when working with distributed databases is always make sure that you apply retry logic to your application and make your statements idempotent so that you can run the same transaction at the same database and get the same result. So let's talk a little bit about topology patterns. There are predominantly 4 patterns with a bonus 5th one. So let's talk a little bit about these. And these are going to be very much US based. So the first one is geopartitioned replicas. And this is the ability to constrain data into individual regions. So in the example here, we have US West, US Central, and US East. What we can actually do is say that all of the user data that is supposed to be in the west side of the US has to live on the 3 nodes that are in the west side of the US. Same for the central, same for the east. Now this has 2 benefits. It'll give you really fast read-write access within the region itself, but it'll give you slow cross-region reads and writes. So a west user can still hit an east, can still read from the east nodes, but they have to deal with that network latency. However, if a west user wants to retrieve west data, which is more common, they will get really fast reads and writes because we have eliminated all of that cross-American latency there. But it does beg the question, what happens if I lose the west region? Well, the answer to that is you would not be able to access the west data. However, your central users and your east users will be unaffected by that because the quorum operation is done at the regional level at that point. So how do I get more resiliency? People ask. So there's another topology pattern for that, and that's geopartitioned leaseholders. Now a geopartitioned leaseholder, with this one, we still put 1 copy of the data in each region. So we're not constraining the data itself to the individual regions. What we're doing is we're putting 1 copy of the west data in the west, 1 in central, and 1 in east. So the quorum operation, you get slightly slower writes because you now have to write to the west for the west plus 1 other region, which the quickest region in this case is likely to be central. So your latency of writes becomes the quickest of your 2 regions. But what we can do with this one is we can actually pin just the leaseholder or the raft leader. to the US West for the West users. Now that gives you extremely fast reads. It gives you the additional benefit of being a little bit more survivable, because if the West goes down, then we can still go to the central and still use the central region to service West users. So yeah, that's the big benefit of geo-partitioned leaseholders. It really speeds up your reads, or it still allows you to have really fast regional reads. Gives you the extra resiliency of having your data spread into multiple regions, but that comes at a cost of slightly slower writes. You can get around some of these limitations with something called duplicate indexes. So an index in CockroachDB is treated the same way as a table. So it's just a key value store in the back end you have to remember. So if you have a static lookup tables, for example, then you can replicate that index across all 3 regions if required. And this is what we call duplicate indexes. And again, that will give you fast regional reads for the current data. It'll give you a slower cross-regional writes at that point. This is super useful if you have things like postcode lookup tables and things like that, because it'll mean joining to those tables and those indexes become a lot more efficient no matter what region you're trying to join to. Follower reads is one that I mentioned earlier. And again, this is a really useful feature where you can accommodate some staleness in your data. Again, the data will always be consistent. It just may be up to 4.5 seconds stale. And this allows you to read from replicas rather than having to go through the raft protocol and hit a leaseholder to service a read. Follow the workload is by default what is offered by CockroachDB out of the box. What this will do is try to automatically move the leaseholder for you to where the traffic is coming from. So if we take this American example, for example, we will still put one copy of the data in different localities to ensure that you're as resilient as possible. But in the morning, for example, the US East guys will get up and start hitting traffic. So we will put the leaseholder in the East region. And then late at the night, when the West users start using the application more, we will automatically move the leaseholder over to the West Coast. And that gives the West Coast users the best experience there. So the database will try to optimize depending on the workload patterns that it sees as users are using the databases. So let's dig into that sort of latency equality and what effect this has on latency. And the numbers that I'm going to show you are actually real world numbers taken from Google's infrastructure. So if you think of the old way of doing things, you have an active database server on the East Coast here, and you have users on the East and West Coast. So if you look at the read and write response times or round trip times here, for a read for the East or for a write for the East user for that matter, it's around 5 milliseconds. For the West Coast user, it's around 75 milliseconds because he has to travel across America to actually get that. So the inequality in latency there is around 70 milliseconds. What normally happens is you normally don't have a single server because that's a single point of failure. So you add asynchronous replication into the mix or some sort of failover mechanism so that you can recover from a disaster event. But what does this do for your latency? Well, the short answer is it doesn't do anything. It just adds a little bit of complexity because if something did happen to that initial server, you would have to configure some sort of failover mechanism to repoint the applications at the other node within the cluster. And then you would also have to figure out a way of resyncing the original database when it comes back up to make sure everything gets up to date. So as you can see, it's very complex, and you have to consider things like recovery time objectives and recovery point objectives to achieve some business continuity goals. But in terms of this slide, it does nothing for the latency or the user experience then of the West Coast user. So if we look at how we would deploy this with CockroachDB, so we would go 3 regions because again we're a quorum-based system. We have to work in sets of 3 to ensure consistency and resiliency. So in this case, your East Coast user knows its read time is 5 milliseconds, but his write time is slightly more because he has to write to 2 different regional locations instead of 1. But the West Coast user gets a lot better of an experience in terms of its read. So he gets exactly the same as the East Coast user, because we can put a leaseholder in the West Coast for him so he gets exactly the same experience. So the inequality for the read there is exactly the same. We're in perfect territory there in terms of 0 milliseconds for that one. The write workload, again, is slightly better for the West Coast user, down from 75 milliseconds to 65 milliseconds. And that's because that central, or I don't know what state that is, but that backup region is slightly closer, so you can get a slightly quicker quorum operation there. We could take that a step further and we can add another region. So if we had a 4th region closer to the West Coast user, and this is where things really get a lot better for both the East and the West Coast users. So now you can see the inequality there is exactly the same. So the West Coast user is getting exactly the same experience as the East Coast user, which is extremely quick read response times and still really quick write response times as well in terms of 17 milliseconds. However, there is a problem still here, or we can actually make this slightly better. What happens if one of those West Coast regions goes down completely? Then we're back into the same situation as the previous slide, as this slide. So we've lost that region, and then the write latency goes back up again. So the fix to this problem is we add a 5th region. And a 5th region will prevent, so if we add it in the central region, which is the midpoint between East and West, even in the event of a failure now, you've cut the latency in half. So the inequality remains exactly the same for the East Coast and the West Coast users, with additional resiliency as well. How do we actually do this in terms of SQL? I've thrown this in because we often get, yes, but that must be really complex to actually implement. So these slides haven't been updated for the new release 21.1 yet. It gets even easier in that release. So I'll tell you how to do it in previous versions, so 20.2 and before, and then I'll give you a little bit of an insight on how to do it in 21.1. So as you can see, it's just a SQL statement in this case. So we've created a customer table, but what we've done is we've partitioned this table by a column called locality. That column has also been added to the primary key, which is a requirement to do this geo-partitioning. So you can see for a West partition, we're using US West 1 and US West 2 values. For Central, it's US Central 1, and for East, it's US East 1 and US East 4 values. So those partitions, what does it actually mean to partition the data? So remember those ranges that we talked about earlier? What we actually do when we partition is we say that only values with US West and 1 and West 2 can live in the same range. So even though we still lexicographically order everything, we constrain, or we say that West data can only live in West ranges, Central only in Central ranges, and East and only in East ranges. What we can do then is we can give constraints, or we can apply constraints using something called zone configurations. So when I start my West 1 and my West 2 nodes, I give them a locality flag, in this case plus region equals West 2 and plus region equals West 1. And what we can say is I want 1 copy of my data in West 1, 1 copy of my data in West 2, and I want 1 copy of my data in Central for resiliency purposes as well. But we don't apply any leases to the Central region for the West Coast partition. We actually put a lease preference for US West 2 and US West 1, meaning your application predominantly will be reading from those West regions rather than having to go to the Central region. Now that's just a preference. If something did happen to one of those regions, we could still move the lease automatically to the Central region if required. And then the same constructs apply for the Central and East region as well. So next scenario in that case is you may have a West Coast user that is living in California, but he decided to up and move to New York, for example. So how do we move that data from one locality to another locality? It's quite easy. You just have to update the locality column within the database within the user's new locality. So in this case, changing it from US West 1 to US East 1. And CockroachDB will automatically move that row to the correct range on the east coast of America. So next, we're going to talk a little bit about transactions. I'm going to go through very high-level transactions here. And then I will provide you with some reading material when the deck gets circulated after this webinar for you to go and read a little bit more into that. So transactions in CockroachDB are always ACID compliant. ACID gets thrown around a lot. What people actually really mean when they talk about ACID compliance is the consistency and isolation level. So as I mentioned, we run in serializable isolation to ensure consistency of the data and accuracy of that data. So let's go through how a typical distributed transaction works in most distributed database technologies. And then I'll give you a little bit of background of how we at CockroachDB have made this a lot more efficient. So in this case, we're going to insert two dogs, Sunny and Aussie. So typically you would have to go to a leaseholder for the first value, which is Sunny. We'd have to obviously get quorum, so it gets sent out. We'll get an acknowledgement back. Once that acknowledgement is back, we can start the second value in that transaction, which is Aussie. And then the same process happens for that. We have to get quorum, we get acknowledgement back. And once we get an acknowledgement back that it's been written to the ranges of at least 4 replicas in this case, so 2 for the first value and 2 for the second value, we will commit the record back and then back to the client to say that it's been successful. If you think about that, that's a lot of back and forth in terms of network hops. So what did we do at Cockroach Labs? We came up with a feature within the product, or 2 features actually, called lazy transaction records, which allow us to defer writing initial transaction records and do things in a more distributed fashion. And we can do that because of something that we call an existence of a write intent proves the existence of a transaction record. We also developed something called write pipelining, which allows us to asynchronously perform writes while maintaining consistency as well. And we do this by waiting for in-flight writes before we commit, essentially. So everything is done on the wire and then sent back to a gateway node to actually solidify before we send that back to the client and say that it's been successful. So if we have a look at how that plays out in terms of some serialization diagrams, what we'll see here is we're going to use Carl and Nigel as the values. So in a typical serial transaction, you'll send a transaction through as pending, you'll get a response, you'll have to say that I've received that response, so it's a handshake type of thing. It goes back and then you start the Nigel transaction and it's the same process. You'll get a commit and then finally it'll come back after the commit and say great. So that's 1, 2, 3, 4, 5, 6, 7, 8 8 different network hops that potentially has to happen to write 2 records within inside of a single transaction. Seems excessive, but that's the cost of doing things like 2-phase commits transactions. So if we apply our features called lazy and pipelined, what we can actually do is send Carl and Nigel out as independent. We can wait till they both come back as in-flight transactions. Once we have them back, we can update the distributed commit marker, and then finally it gets back to the client once we've updated that commit marker. So that's 1, 2, 3, 4, 5, 6, but 2 of those are done in parallel rather than done in serial mode like previously stated. So we've already cut the networks hopped down there by 1/3. So we did go one step further, and depending on how you set up your transactions, we can leverage something in CockroachDB called parallel commits. And this uses lazy transaction and write pipelining to get down to 2 round trips. And then if you include what we're calling a staging distributed commit marker for multi-batch inserts, we can actually get that down to the theoretical minimum limit for a distributed transaction. So let's take a look at how that looks. So you fire off Carl again, you fire off Nigel again, you fire off a distributed commit marker all at the same time. Now Carl and Nigel just have to update that distributed commit marker, and all three of them come back at the same time, and we will acknowledge that back to the client. So it's only committed once all operations are complete, and we've basically replaced the centralized distributed commit marker, the centralized commit marker with a distributed commit marker, which allows us to do all three of those things in parallel. There is a lot more information on hows we've done that in the links that are in this deck. So I do encourage you guys to go out and read through some of the documentation and blog posts that we have available with this. So I'm going to go through, just do a time check. What have we got? 15 minutes, yeah. So I'm going to take 5 minutes just to explain how we're actually doing SQL to the key value mapping for you to better understand how indexes are structured and things like that in CockroachDB. So if we think of a tabular data store, like something like a SQL Server or Postgres, there are columns and rows. Although a primary key is not required in those technologies, it is absolutely required in CockroachDB. If you do not assign a primary key, then one will be assigned for you, and it's normally put as a row ID with a unique row ID by the default. My recommendation is always to apply a primary key where possible. So let's take an example of how we do this encoding then to the key value store. So on the left side of the table there, you can see the actual table as it's represented in a normal tabular format. So we have an ID column, we have a name column, and we have a price column. When we move to a key value store, that becomes a key, and then the value becomes BAT and the price, 1.1. So it gets encoded in a way that is efficient to do the distribution of the data. How it's encoded, so if we look at the key, it's basically table name, index name, and the key value. So in this case, it's inventory, it's the primary index, and the key is 1. This is why it's always more performant to do a key lookup than it is to do a range scan, but that's the same with any database technology that you pick. So I often get asked, how do secondary indexes map to that? I think one of the Erlang employees, Carl, asked me this. So the short answer is it's exactly the same. We encode it in exactly the same way. So you have table name, index name, in this case value, and the key for that value. So you're still using a key value indexing structure here, and you retrieve the data in exactly the same way. That's just showing where you add an index. In this case, you're adding a 4th key there with BAT again with a new price. So where can you guys learn more? There's plenty of resources out there. I would highly recommend our documentation. It's very thorough, it's very complete, and we have an extensive documentation team that are very proud in the documentation that they produce. And I can live and I would live and die by it because it's really, really good. We have a blog which you guys are more than welcome to follow as well, and we have a community Slack channel if you want to get into the community spirit and start sharing ideas and knowledge when it comes to CockroachDB. We have a lot of our in-house engineers that monitor that chat as well. So if you come across any issues or problems that you're experiencing while developing against CockroachDB, it's a super useful resource to go and ask those types of questions. In terms of a more structured and curated approach, we do have something called Cockroach University, and that is a curated list of courses that will get you up to speed with CockroachDB very, very fast. There are a couple of different courses on there, from getting started with Cockroach, architecture courses, and then there are more developer courses around Java and Python and things like that. So I would highly recommend that you guys go and take a look at that. But that is the end of the deck. So I hope I've left enough time to answer any questions. And I do encourage you to ask questions, guys. I do like to be interactive in these sessions. So yes, I'm ready to take the questions.
Perfect. Thank you so much, Daniel. That was super helpful. While we wait for the first set of questions to come in, I guess I'll remind attendees, as always, we'll be sending you out an email with all of the links that Daniel just shared, the slide deck, and this recording, so you can watch anything else in greater detail. And a reminder again, we are accepting questions on both Twitter and via GoTo in the questions tab. The first question that we've got come through is, how does Cockroach interact with some of the Erlang tools such as Ecto and Postgres, and are there plans to expand or change any of that?
Yeah, absolutely. It's a great question. We're getting a lot of people asking for support for Ecto. So it's top of our. We have an internal team at Cockroach that we call the third-party tools team, and it's the next on their list to do some investigation around what it's going to take for us to fully support Ecto and things like that. Now, that being said, remember that I did mention at the beginning that we are Postgres wire compatible. So providing you have a Postgres wire or a Postgres compatible driver as part of the Erlang framework, you can still use CockroachDB, and I believe we are engaged with some of the Erlang developers that are actually working with clients and working successfully with those drivers as well.
Perfect. That is super exciting to hear, and I'm sure an answer that the asker will be happy to hear. A similar line of questioning, actually. This one says, you mentioned a new release recently. Are there plans that you're able to share about views for future features or future roadmap details that you're able to share?
Yeah, absolutely. I mean, we don't shy away for questions like this. We actually encourage people to start digging into what our future roadmap is and things like that. So the latest release that came out made doing the geo-partitioning stuff a lot easier. So rather than having to go through setting those constraints, like I mentioned in the presentation, you can literally say now, I want to create this table and I want to make it regional survivability. So create table X, regional by row or regional by table or regional or just regional. So it makes it very simple. So we've tried to simplify it for developers to deploy in more of these multi-regional type setups, because a lot of traction is being seen in that space. In terms of roadmap items, we're doing a lot of work in the geospatial area as well. So we recently supported geospatial indexing and things like that. So we're continuing to invest in that as well. And we're continuing to invest in third-party tooling as well, similar to what I mentioned around Ecto. There are a number of ways that you can consume CockroachDB as well. So you can, obviously, customers can self-host CockroachDB and either use a community edition or an enterprise edition with licensing and some additional features and things like that. Or the third way, which I haven't touched on yet, is they can adopt something called Cockroach Cloud, which is a fully managed and fully managed platform as a service type of offering for CockroachDB. Now, there are two versions of that. There's something called a dedicated tier, which you get your own VPC, you get your own Kubernetes cluster that runs your own CockroachDB implementation. That can be single or multi-region. And then in January, we launched a free version of CockroachDB, which is a serverless multi-tenancy type of adoption point. So if you guys want to go away and spin up a free CockroachDB cluster, absolutely recommend you to do that. In terms of the plans or the future roadmap, and this is where it gets really exciting from my perspective, is we are planning to increase that serverless tier to be more of a paid offering. So we're gonna, at some point this year, we're gonna be launching full serverless CockroachDB in the cloud, where you only pay on a consumption-based model. And again, further down the line, we will make that multi-region as well. So our roadmap looks kind of like that. We will always continue to add the more features in terms of Postgres compatibility as well. But yeah, I hope that gives you some idea of where we're thinking of going.
Yeah, that's a great answer again. This question is, suppose the replica that did not receive a write as part of the quorum becomes the new leaseholder after a failure. How can CRDB guarantee that this new leaseholder has the most up-to-date version of the aforementioned right?
Yeah, that's again a great question. So with CockroachDB, what you're essentially asking there is how do we prevent split brain, or is more commonly known as split brain within database technologies, and that's protected by the Raft protocol itself. So the transactions that are in flight are all bootstrapped off the top of the Raft protocol. So there are constructs within Raft that says if there are inconsistencies that we can't resolve because of a failure or a new leader election, we will throw an error message back to say, again, you need to retry until we can get a consistent answer and we know the data is in a consistent state. That typically happens after the leaseholder election has taken place, and then we can confirm via checksums that are done and bootstrapped off the Raft protocol to ensure that consistency.
Perfect, thanks for that. And I think we have one more question, unless anything comes in while you're answering it, and that is, I currently work at a financial service offering or fintech. What are the benefits for fintech organizations in moving to CockroachDB, and are there success stories that you can talk about?
Yeah, absolutely. I mean, there are a lot of benefits in the fintech space. As you can imagine, we're seeing a lot of momentum in that space. And it's predominantly around the consistency of the data. I've worked in many financial institutes in the past, and typically they are all bound or still in some form using things like IBM mainframe. So you have to think of why are new fintech companies still looking at that IBM mainframe technology, which is what, 30, 40-year-old now. And it's because of the serializable isolation level that the mainframe offers. So it can guarantee consistency. So when you think about financial transactions, for example, you need to be absolutely sure that the data that you're reading and writing is accurate at all times. Because if I'm looking at my bank account, I don't want to see what the data is, 50 milliseconds ago. I want to see what it is now. So you'll get that same consistency that an IBM mainframe used to offer you. But the biggest benefit you'll get on top of that is you'll get scalability. So for example, if you're a really new fintech that needs to start small, you can start CockroachDB with as little as 3 nodes. So spin up those 3 nodes, get using it, deploying your application, being very agile, and then as you adopt more users, as your workload starts to ramp up and you get more concurrent requests and connections and things like that, you simply add more nodes to CockroachDB, and we will, because we are linearly scalable, meaning you add 3 nodes to an existing 3-node cluster, you've already doubled the capacity in terms of storage, in terms of performance. So it's a very predictable model that you can come up with when scaling.
Thank you so much. That's the last of the questions that we've had come through. Thank you everybody for joining. Thanks again, Daniel, for helping walk us through this. As mentioned, check your inbox. There will be the recording, the slides, and a couple of links to various ways that you can learn more about CockroachDB or get help implementing it. Until next time, I will talk to you then. Thanks for joining us and take care.
Thanks. Bye.